All right then. So good evening, good evening, good evening. It is I, hitherto, once more. Welcome back, everyone. Let's put the AC on because just like AJ says, it gets kind of hot in this room. Welcome, welcome, welcome. Hey AJ, good to have you, David, Marcelli, and Prince. The whole gang's back together. Yes. How's everything going? A bit of a table setting as we get going. Hope you've had a good week. Hope you've been up to all sorts of good, and we'll be ready to go in very shortly. Just put that to one side. Oh, wonderful. It's Good evening, Marcelli. Good evening, Prince. Good evening, David. As well. I caught wind of your sessions yesterday. Here they're doing really, really well. I heard that you had someone who was showing off, I believe, or had some kind of a website to show. So good news on that side. Yeah, website building is ever more present, ever more easy, I would say, especially for those that are now coming into this, having seen the academy material and wanting to get going with building something. There's a lot of material I'm going to show you towards the end if you stay with me about website building. It's just never been easy. It's not that hard to get something up online on the internet, so to speak, and to show off your work. But what these sessions are all about is, aside from also talking about this, is I want to get into more of the field of AI with yourselves and really talk about some of the more computer science principles we've been discussing thus far. So if you stayed with me from last week and the week before that as well, we've been talking a lot about kind of computer science principles in terms of algorithms and also discussing them inside out. So we can eventually get to the point of understanding the internet, understanding the tools of the trade to then go off and build your CV website and do something with it. What I was going to do today is actually just go through a just set of instructions, which I just remembered. I do have a handout I'm going to send over to you before I forget. I'm not getting a sticky note here telling me to go and send it off. So yes, perfect. All right, wonderful. If anyone does join in a little bit later or doesn't know what I'm referring to, I'll just send that again in the chat when I need it, in case I can't go up and revisit. For whatever reason, I can only reply to my own message in the Zoom chat, but I trust if you scroll up, you'll be able to find it there. Regardless, okay, so what we're going to go off is dovetailing what I was talking about last week, where we talked about algorithms and really just being as a step-by-step instructions for solving some kind of a problem. As many in the case of computer science principles, we're just trying to reproduce some effort, and then not unlike this problem I had last week of looking in the phone book and then finding Mike Smith amongst all the other phone book names and numbers. But up until now, we've really only been focusing on those step-by-step instructions and not so much on how the data itself is going to be searched, on how it's going to be stored and the like. And of course, in this version of that problem, it's going to be stored again on paper like in a book, but in the digital sense, and the computers, of course, it's not going to be on paper. It's going to be a bunch ones and zeros. But it's one thing for us to say that the numbers and maybe even the names are ultimately stored as ones and zeros. But what do I mean by that? What exactly is that? There's of course all these kind of transistors that are then switching on and off. But with respect to each other, how are those numbers then laid out from left to right, top to bottom? Are they all over the place? So let's actually have a look at that and then consider that question now of how a computer uses what we call data structures and to help and facilitate the implementation of those algorithms, whereby how you lay out a computer's data inside of it has memory. It has then some non-trivial impact on the performance and the efficiency of your algorithms as well, where the algorithm itself can be either correct, as we've seen, or not as necessarily efficient altogether, not logically the right way. Okay, both in terms of space and the representation underneath the hood then of your data can have a real significant impact. And so that's what I want to get into. But first, let's just simplify the world, I think. If we can really focus on what I have on screen here, instead of say like a whole phone book of names and numbers like I had last time, but this time I just want to focus instead on numbers. Okay, why did that go off? Ooh. So if I just simplify it into just numbers, and I'm looking for one particular number, even much smaller numbers than phones this time, but actually just integers alone. Let's say I have 7 of them at this time, okay? And what I've got on screen then is these 7 numbers, if you will, behind these kind of 7 doors, okay? And so what we're going to do is going to knock on each of these doors, opening them one at a time, and really reveal what's behind them all the time, like a game show. And the goal at hand, again, is what I'm telling you is to find a very specific number. What we're trying to find then is 50. So just like I saw one specific phone number last time, this time I'm trying to find one integer, 50 specifically. Well, okay, so where do we begin, okay? If that goal is to find 50, I'm just going to go pick one at hand and go with the closest one to me. Knock, knock, knock. Who's there? Well, it's 15. Okay, 15 is the number, so a little bit low. Still, remember, we're looking for 50. So let's proceed from here. If I go on to the next one to see 23. All right, we seem to be getting closer. Let's try and open the next door then. Oh, no, so we've sort of veered down smaller downhill, so I'm a little bit confused now. But I still have 4 doors to go on left and check. So 50 is not here. Neither is there. 42. 50, in fact, is there. Yes, ding, ding, ding. So not bad. What we're saying then is within 1, 2, 3, 4, 5, 6 steps, I have found that number in question, okay? But of course, we've only, there were only 7 doors. So if we generalize that to say then that if there were like n doors, where, that was roughly n doors I had to open amongst all the n doors just to find the one I was actually looking for. So could I have done better, is my question. Good evening, Anchor, as well. Just a whole host of people joining this evening. I just seen Anchor and Manpreet as well. Jake as well. Good to have you. So if you're following along, my instinct is a bit like yours, where we wanted to start perhaps on the left of the screen and then move over to the right. We seem to be on a good path initially. I think for those first couple of, we went from 15 up to 23, and then like if you 16 like clearly is a wrench in the works because I expected it, perhaps naively to be bigger and bigger and bigger and bigger and bigger as I moved over to the right in order for my quest to 50. But honestly, had I not told you anything, and like I didn't tell you anything before this, like you wouldn't have known anything about the numbers other than maybe, the number 50 is actually in there somewhere. If I told you nothing behind what's behind the numbers, as to maybe the magnitude or maybe the size of any of the numbers, let alone the order, it would be quite difficult to find. So, back in the world of the phone book, remember from last week, of course, we were able to take for granted that those names in a phone book, like the yellow pages, were sort of sorted by like the company or the name first, like A, B, C, from left to right, A to Z. But in the case of like the data, if your data is just added again to your computer memory, one at a time in a particular order, then the onus is going to be on you, the programmer, the algorithm perhaps, to actually find that number you're interested in nonetheless. All right, so what's left there? Let's look at them. Yes, number 4. Indeed, like 4 was even way more than 50 still. So again, we had 7 doors by design, and I randomly generated a number for them. So you could do no better really than that. Okay, I might have gotten lucky. I could have got it the first time around. I might not have gone with my initial instincts and touched 15 first as left. I might have effectively just blindly gone and just touched 50 and then just gotten lucky, first time around, and then it would have been just one step. But there's only a really 1 in 7 chance I could have been correct so quickly. So it's not really an algorithm that I could reproduce with the same efficiency again and again and again, which is what we're sort of trying to get to. Okay, how can I do better? Rather than having a 1 in 7 chance, how does a phone company, how do the Yellow Pages enable us to do better there? Well, of course, like the Yellow Pages and kind of like the phone book, puts a huge amount of effort up front just to sort all those names, and those associated numbers from left to right, from A to Z. And then that's a big leg up for us, I suppose, because I can assume at least we can divide and conquer, so-called the binary search we saw last week. We kind of divide the phone book in half, and then I kind of chop off half of it, and then sort of go again half and half and half, and sort of like a bouncing ball, if you will, until we eventually just get to nothing. And then binary again, implied by the by, as in binary, that's halving the problem again and again. So that was our binary search last time. Again, someone's going to do that work for us. And we're assuming that that's going to be in an ordered list, be it the phone company, be myself again with these phone numbers again. So we can't rule out the possibility that they're randomly assigned. Let's take one more stab at the problem. But this time I'm presuming that the 7 doors in question do in fact have numbers behind them. They are sorted again from left to right, small to big. So again, taking the binary search from last time. So where do we find 50 now? If I'm looking for 50 and I have 7 doors at my disposal with which of those same numbers again, but this time I'm telling you up front, like you would expect in a phone book, that they are sorted. Like a dictionary is going to go from A, B, C, D, E. I know, skipping ahead thinking, okay, well, I remember that the other numbers are there, so I immediately know what 50 is. Let's just assume for the moment, okay, that, clean your eyes, bleach your head. We don't know anything about the other numbers other than the fact that they are sorted. I have sorted these numbers. So my inclination is maybe we don't start with this door like we saw last time. Much like my inclination ultimately with our phone book, if I'm looking for someone that begins with the letter S or M for Marco, I'm not going to go through A and then B and then C and then D and E, but I'm going to go somewhere like in the middle of the book, somewhere in the middle. And then indeed, that's what I'm going to do here. So just like in a book, just like in a dictionary, I'm going to go in the middle of these doors and say, 16. So it's not quite the one I wanted. But again, if I'm telling you outright, we know one thing for certain, that the doors are sorted. They are in order. I know that 50, again, from left to right, top to bottom, is not going to be down here somewhere. We can kind of rule this out altogether. So I'm really only going to be looking off to the right. Well, where do I go to the right? I have 1, 2, 3 doors left, and I'm going to follow the same algorithm and just open that door in the middle, so to speak, this one here. And, so close. I found only, if you will, the meaning of life, 42. So 42 is not the number I care for, not the one I'm looking for, but I do know something about 50. 50 is bigger than 42, and so, it's quite simply the case then that I've divided and conquered, and okay, it's going to be that last number out on the right. So how many steps? Remember, like before, it took me up to 6 steps to find that number 50, and then only by luck really did I find it, because it was just going to be randomly placed. It could be 7, But I now spent 1, 2, and just 3 steps in total. 3, which of course is like far fewer than 6. Again, and these numbers and these doors just grow in size, and I start to have hundreds, if not thousands, of millions of doors. Surely it's going to be the case then that just like the dictionary or the phone book of halving that problem again and again and again is going to give me that answer if it's there in the logarithmic instead of linear time, so to speak. Yeah. But what's the key to success then? This algorithm, this binary search, is that the doors are not only sorted, but they are back to back to back. Now, I have the luxury of designing this PowerPoint, and I can move back and forth and kind of put these numbers where I want to. But even then, for me to put this PowerPoint together, it did suppose some amount of time, some amount of energy. But fortunately, such a step just takes kind of 1 unit of energy, if you will. Okay, and then I can immediately jump wherever I would like to, 1 step at a time. But a computer, what we know about machines is that they're purely electronic. And in the context of memory and electricity, it doesn't actually need to take any steps. Like electronically, a computer can just go and jump to any location in memory instantly. And we call that so-called constant time. So like 1 step at a time, it might take me several. So that's one advantage that the computer has over me with my flesh and bones, is that, it's just one of the reasons perhaps why they're so much faster at us at solving so many types of problems. But again, the key ingredient of this is laying out the data for us, for the computer to solve ultimately your problems quickly, is that you need to put your data back to back, back to back, back to back in order, okay? Because a computer, at the end of the day, yes, only stores zeros and ones, but those zeros and ones, they generally going to be treated in, say, units of 8 bits per byte or 8 bytes. But those bytes too, when storing numbers like this, those numbers need to be back to back and not just jumble all over the place. Because so it needs to be the case then that the computer is allowed to do the simplest of algorithms to figure out where to even start to look. Even I, in my head, I'm sort of doing a bit of maths. I'm thinking somewhat, even lightly. I'm figuring out, well, what's the middle? I've got 7 things here, 7 doors to look through. Even just amongst a few of them, you can pretty much just eyeball this quickly. But still, there is some thinking there for to be done. If a computer has to do that kind of arithmetic, so what is that maths? How does a computer think about this? Well, if I'm telling you that I have 1, 2, 3, 4, 5, 6, 7 doors. Initially, okay, and I want to find maybe the middle one of the 7 doors. Well, you know what I'm going to do? I'm going to do 7 divided by 2, which is going to give me 3, 3.5. Yeah, and that's not an integer. That's kind of useful or good or great for counting doors, but let's just round it down to 3, okay? So that's what I'll do. 7 divided by 2 is 3.5. Rounded down to 3 suggests that mathematically, the number of doors that's kind of in the middle of my 7 doors should be right here. 3, okay? 1, 2, 3, that, okay? Now recall that computer generally starts counting at 0 because 0 bits represents that 0 in decimal. And so this door is going to be 0, 1, 2, 3, and then there's still a few more days left, so that's 4, 5, and 6. But again, the first door is going to be 0, and the last one is going to be called a 6. So if I'm looking for number 3, that's 0, 1, 2, 3. That's why I jumped to the middle of the doors, because I very specifically wanted to go to location 3 in this. Well, why after that did I jump to 42? Of course, remember, so that was, so I rolled this out, I knew that I had 3 remaining doors left. Of course, I was in the middle of the 3 remaining doors. How could a computer then know mathematically where to go? Whereas we can just kind of eyeball it, there's only 7 left. Well, again, if I've got 3 doors, and I'm going to stop disappearing now. So if I've got 3 doors left, and I'm going to say this is index 0, 1, 2, 3 was my first choice, 4, 5, 6. Of our remaining 3 doors divided again by 2, you can clearly say that's going to give me, well, 1.5 each. Yeah, but let's just run that down to 1, shall we say. So now if we renumber those doors, as we did before, so 0, 1, and 2, because again, these are the only 3 doors that I know left exist that could contain the number 50 inside, well, 1 is going to be 1, 2, that's a 42, and then that's how the computer then knows to jump right to 42. Of course, like, I've only got 1 door left. It's pretty simple. In that case, I can clear the board and just say, I've only got 1 left. You know, I don't even need to do any of that maths. If it's just 1 left, just pick it up, and then so we can immediately access that in constant time. In other words, like, even though my thinking, you know, my human hands here have to take a bit of time and energy just to get from one door to the other, a computer has a leg up, so to speak, of getting to those doors even quicker, because all it has to do is a bit of division, maybe a bit of rounding down, and then jump straight exactly to that position in memory, so to speak. Yeah? And that's what we're going to call constant time. But again, this presupposes, again, that all that data, all that we've seen thus far, is data is laid back to back, kind of consecutively, you know, so that everything, all these numbers, you know, are going to be an equal distance from every other one too. Because otherwise, you know, if you were going to do this maths and come up with the numbers 3 or 1, you'd have to be able to know where you're jumping to in memory exactly, because that number 42, it can't be down there. Like, it has to be numerically in order to be where you expect it to be. And so this is in computer science, or like in programming more generally, this is the kind of arrangement where you start to think about your ones and zeros, your doors really in computer science, really is going to be representing your data. We'll see that in a second. Back to back, your data is going to be called an array. So we call this an array in computer science. An array is really just like a block, like a contiguous block of memory where values are stored kind of back to back. And there are types of arrays within that, okay, from left to right kind of conceptually. Although, of course, you know, direction has less meaning once you're inside the computer, like what way's up and down. But now the arrays, again, thanks to the arrays, which you're going to see examples of in a second, we're then able to perform searches inside of them, you know, like even within the phone book so quickly. Even after all, like if you imagine in the physical world, if you get a dictionary or a phone book, it's not that unlike an array, you know, or albeit a bit more of an arcane version here, because the pages in a dictionary are going to be back to back, from left to right, you know, top down, which is wonderful. And if you remember, when I searched through the phone book with you, we were already immediately able to describe the efficiency of the phone book via this divide and conquer, you know, mechanism, by those 3 algorithms we saw. We tried 1 page at a time, so like page 1, page 2, page 3, page 4, but that was very long. Then we tried 2 pages at a time, page 0, 2, 4, 6, 8, and so on, and then the 1/2 for the remaining problem at a time. It turns out then that there's actually a direct connection to even the simplification of the same problem, where if I have n doors and I search for them from left to right, that of course might take me as many as 6, 7 total steps, or n, if the number I'm looking for is way at the end there, this one here in blue. You know, I could have done maybe 2 doors at a time. Perhaps I could have done the same thing as we saw last week, of skipping a step or skipping a page. I could have gone from 0 to 2 to 4, and then, you know, although that could have worked here, it would have cut back the time. But although that would have really gone off the rails then if I actually started at, you know, the wrong number, I missed it. Or perhaps if it wasn't even, if they were just randomly sorted numbers. Again, because there would have been no logic to me going, you know, left to right twice as fast, because I would be missing over every other element of the list without knowing where to go back to. So in the case of a binary search, where, you know, my last algorithm I went through last time was, in a binary search, by meaning 2, we start in the middle, we put that into 2 halves, we found kind of 16, and then, you know, started in the middle again, divide and conquer, and then found 42, and then really started in the middle again, and there's only 1 left to go. I found my last number, job done. So binary search is quite similar to what we did last time, of just tearing the problem in half and starting again. But my proposal to you, what we're going to see this evening, is a few other examples of that. So how do we describe the efficiency of the algorithm last time, of the binary search? Well, again, I proposed that the algorithm was linear. So this linear line in red here represents, again, by the level n, because every page in that phone book, in the dictionary, like in the worst case, you might need 1 extra step to find someone like Marco in the middle of the book. Indeed, like that in the case of the doors, if there's only just 1 door ahead there, you just kind of, you know, need to go 1 extra step to find that number, 50 or any other number. Now, I could, once those values are sorted, you know, I could go through them twice as fast, kind of like 0 index 1, and then 4, and then 6, and then 8, and 10, you know, looking 2 doors at a time. And if I go too far, if I miss one, I could, you know, if I go to 51 perhaps, I could then double back and then fix that mistake. But ultimately what I did, I chose to divide and conquer, which is, again, starting in the middle, and in the middle of the middle, and in the middle of the middle of the middle, and then that's what gave us this performance you see at the bottom. So this so-called logarithmic time, log base 2, you know, even with, if nothing else, means that we have a different shape fundamentally, okay, to the performance of that algorithm. It just grows so much more slowly, and the problem gets, you know, so much bigger. Even if it gets drastically larger, you know, even off the screen there, imagine if n gets huge, that green line wouldn't seem to be going very, very high, even as much as the yellow or the red ones do. So again, in computer science and in programming, there are actually a few formal labels that we can apply to this kind of methodology to solving problems. And amongst which, when we talk about the upper bounds as to how much an algorithm can take, you might say this, quite literally, it's called big O. So big O is, well, that an algorithm is in a big O of some formula. So for instance, amongst the formulas it might be are these, like n squared, or n log n, or log n, or 1, you know, which is to say that you can represent somewhat simply mathematically using n, or really just any other placeholder, as your value, a variable that represents the size of the problem in question. So for instance, in the case of a linear search, where again, I'm looking for the phone book from left to right, up to down, I'm searching from the doors left to right. In the worst case, it might take me as many as n steps to find Marco, or 50 in the door case. So we would say that the linear algorithm is a big O of n, which is just a fancy way of saying, quite literally, like that's linear in time, okay? But sometimes I get lucky, you know, sometimes like that would be the best case where I win the lottery, you know, I might find Marco the first page I pick up, or, you know, I just open 1 door, I get there right away. You know, anything that's, anything that's faster there, And computer scientists will also have ways of expressing lower bounds on running lines and times of algorithms, whereby in the best of case, perhaps, like an algorithm might only take this much time and at least that much time. And so what we use then is a capitalized omega to express that notion of a lower bound, where again, like big O represents the upper bound on the same one, then omega is the lower. So we can use the same formulas again, depending on the algorithm. It might take n squared steps or just n, one constant number thereof, but then we can consider like a linear search to having a lower bound. Because in the best case, maybe Marco may be like 50 amongst my doors, or any number of inputs of the same problem just happens to be very at the beginning of that book of those doors. And so in the best case, a lower bound on running time of linear might be omega of 1, because you might just get lucky. You might just take 1 or 2 steps, or 3 or maybe 2, whatever few amount of steps, independent of the number n. And so we therefore could express that lower bound as well. Meanwhile, there's another one as well, this kind of Greek symbol out there, theta, capitalized here, which represents a coincidence of upper and lower bounds. So if it just happens to be the case for some algorithm that you have an upper bound and a lower bound that are the same, you can equivalently just say not both of those statements, but simply just refer to the algorithm is in a theta of some formula, okay? Now, suffice it to say that the green line, what I'm telling you, is good. Yes, this is what we want, okay? Anytime that we achieve logarithmic time, instead of, say, like linear time, we have made improvements. But we presupposed a few things. I kind of presupposed in both cases, of the phone book and in the case of the doors there, that they were sorted in advance for us. Like the values were in some kind of an order. By me, in the case of the doors, and the phone book in the case of the yellow pages, they've kind of gone A, B, C, D, and downwards. But what did it cost me and what did it cost the yellow pages to sort all those numbers and the names just to enable us ultimately to sort logarithmically? Well, let's consider that then. In the context of, again, some numbers, this time some numbers that I myself can move around, and this took me a while, so work with me, okay? But what I've got in front of you are 8 cups. I love PowerPoint, you can do all sorts of things. These 8 cups are going to be numbered from 8, so all the way up to 8, 1 through to 8, and I'm telling you right now that they are indeed smallest to largest, okay? So I could equivalently do the same problem from, largest to smallest, as long as we all agree what the goal is, whatever it is. But let me just go ahead here and just randomly, there you go, start shuffling a couple of these cups around so that not everything is in order anymore. Indeed, like what I'm doing here is I'm deliberately jumbling these up, and I'm putting them not in the order I want. Some work now needs to be done to put them into order. Now, why did they arrive in this order? In the case of the phone book, new people are moving into a town every day, so they're coming in or themselves not in alphabetical order. Point is to say, it's just seemingly random. So it's up to the pages of the phone book to really put them in the right place in the phone book. Like a new word gets added to the dictionary, put that into the right page of the dictionary, for the sake of next year's prints. Same thing again for the doors, where I want to add more and more numbers behind those doors, more prizes to my game show. I need to decide where to put them. They're not necessarily going to be arriving in as input, kind of the source in the order I want. So this is the kind of thing we would expect. Data can come in some randomly ordered way. So how do I go by sorting my data? How do I get my ducks in the right line? So let's take the first problem I see. Clearly, what I can already make out is 2 and 1 arrived out of order. So what I'm going to do is just go ahead and sort of swap those 2. There you go. So I've now improved the state of my cups. I've made some progress already. Okay, 1 and 2 are now better, but 2 and 6, okay, like fine. Although maybe there should be some cups in between. So let's look at the next pair now. Now we have 6 and 5, which that to me is definitely out of order. So let's switch 5 and 6 around. All right, now, so 6 and 4, still the same thing. Swap those around. 6 and 3, just as much. Now, 6 and 8 are not quite back to back. There's probably going to be some number in between 6 and 8, but they are at least in the right order. Because, of course, 6 is less than 8, and our goal was to go from smallest to biggest. Lastly, then we have 8 and 7. Let's swap those 2 around and, we're done. We're done. Or are we? Well, clearly not, okay? Like, we made some improvements, and with every such swap, we've made better the state of the cups here. But some of those cups remain very much out of order. Now, these 2 are all set, so 1 and 2 are fine. I'm going to say those are, we can work with them. 2 and 5, okay, just as well, even though ultimately we might need some numbers between them. But 4 and 5, yeah, well, that's out of order. Let's swap those around, 4 and 5. Same goes again, 5 and 3, just as much. I'm going to swap those 2 around. 5 and 6 seems okay. 6 and 7, okay. 7 and 8, okay as well. So we're almost done there. But I do see a couple of glitches. Let's just go back to the beginning, rewind. Let's compare all the pairs of cups pairwise, okay. So 1 and 2, fine. 2 and 4, oops, okay. So let's swap 3 and 4 around. Let's just keep going to be safe, okay. 4 and 5, 5 and 6, 6 and 7, 7 and 8. And just by way of this process, again, just by comparing cups back to back, we can then fix any mistakes that we had. So just for good measure, like again, from a computer, I can't really see this top-down perspective. Let me do this one more time. 1, 2, 2, 3, 3, 4, 4, 5, 6, 6, 7, 8, 9. Okay. Now, this time, I've gone all the way from left to right just by checking every single cup was in order. Yep. Fine. I can now safely conclude those cups are sorted. Done. After all, like if I just went from left to right and I did no work, I would presume that if I do the same algorithm again, I'd make any changes. I wouldn't. So I can just quit at this point. I can now safely say, I've sorted my data. Now, that's fine and good, but that's just one way of doing this. Perhaps I could have sorted these a bit differently. It felt a little bit tedious. Again, maybe you watching this along felt like I was doing a lot of work, just cupping. What if I tried to select the cups rather than deal with this idea of doing 2 cups at a time, okay? So there's another way around this, and let me propose then. I'm going to go ahead and just like before, I'm going to randomly shuffle my cups one more time. So there we go. Again, just shake them up in any order. just making sure to perturb what was otherwise from left to right, smallest to biggest. And now we have another random assortment of cups. Okay, they're randomly sorted. But unlike last time, unlike what we just did, you know what I'm going to do this time? What I'm going to do this time is I'm going to pick out the smallest cup I see. So let's go again. 2 is already pretty small. So again, so I'll just start from the left to the right. Let's go and check if there are any other cups that are somewhat smaller than 2 that I might prefer to be in this here location. Okay? So let's go from left to right. 3. Okay, well, 1 is better. Sure, I'm going to make a mental. So just keep this to one side of your mind. 1 is definitely smaller. I'm going to make a mental note of that one. 5, 8, 7, 6. Okay, right. So it would seem to me then that 1 is the smallest number. So what I'm going to do is I'm going to go and take that 1 and put this where it belongs, which is right here at the side for one time. I'm just going to say, make a mental note of 1, put that to, as an aside, and put it back in place. But only that there's no real room for it, is there? You know what? Like, these were randomly sorted. I kind of shuffle these cups up in any order. So let me go ahead and just evict whatever was there, and I'm going to put 1 in its place. Now, again, to be fair, like, I must have messed things up a bit, but no more than I would have had when I received these randomly numbers in the first place. So, in fact, I might even get lucky, just by evicting a cup and putting it elsewhere. I might end up putting that said cup in the right place after all, so it all washes out in the end. So let's go ahead, the same process, the same algorithm as before. I'm going to go ahead and select the next smallest number, but I'm not going to bother looking at number 1 anymore because, that's kind of done. So I'll just kind of wash it out, let's say. Yeah. So let's go through them. Now, number 3. 3 is pretty small, but whatever. Okay, I'm going to keep that in mind. I'm just going to say number 3 for now. 3 is pretty small, so I'll forget about that. Number 2. Oh, number 2. 2 is even smaller, so let's delete number 2. Number 2. 5 is bigger, 8 is bigger, 7 is bigger, 6 is bigger, 4 is bigger. Okay, so it seems then that 2 seems to be the smallest number I can work with. So I'm going to go ahead and select number 2. And I know that number 2 belongs here, but again, 3 is already in that spot. So what we need to do then is evict number 3, move it out the way, and then, hey, I got lucky. Now I have 1 and 2 and 3 in the right place. But again, let's go through the process once more of selecting the smallest number. So this time I see number 3. Okay, number 3. Again, I don't necessarily know, I'm speaking from a computer, that I'm looking at one number at a time. In fact, there could be anything smaller to its side. Who knows? It could be 2.5, 2 point whatever. But let's just check again for the sake of consistency. What else is out there? Let's go and check. 5, 7, no. Okay, so I can safely conclude that number 3 is going to be the smallest one. So I'm going to pick it up. I got lucky. Well, it was in position 0, 1, 2, 3. There we go. So I'm going to leave it alone. Put it right back where it belongs. How about the next smallest number? All right. So by now, I think we all know. But 3, 4, 5. Oh, 7. 7 is going to be smaller. But I remember this. 6 is even smaller. I remember that. And it feels like I'm just creating more work for myself. 5 is going to be the next smallest one. But 8 is all the way over there. So what we're going to do is we're going to pick 5. Oops. I forgot which one's which. Oh, right. So yes, I know 4 comes before 5, but that's all the way over on location 8. So I'm going to do this. I'm going to pick it up and then evict it and then put it right into 5's place. Right then. We know that 7 is pretty small, but even 6 is smaller than that. But still smaller than 7 is 5. Again, so I'm going to pick up 5. I'm going to evict it, put it in that place, and then still 1, 2, 3, 4, 5, 6, 7. 7 is small, but 6 is even smaller. And then even smaller than 8 still. So let's pick up 6. Let's evict 7, put that in its place, and then there you go. Now, for good measure, like we're obviously done. You know as well as I do that we're done. But the computer doesn't know that. The computer doesn't know that yet if we're just looking at one of those cups at a time, or if you insist like one of those doors at a time, one of those data points at a time. 7 is pretty small, 8 is no smaller, so I've selected to stay right there in this place. 8 as well by that logic too. So now it's in this place. And so what we end up with is 2 kind of algorithms I've shown you. And these 2 algorithms that I've concocted along the, there we go, that I've forgot to title. There we go. I've concocted along the way. Actually do have some formal semantics to them. In fact, in computer science, we'll call the first one of those ones this thing here. Okay, this algorithm is called the bubble sort algorithm. Because in fact, if you compare the two cups side by side, if you swap them out on occasion in order to fix the transpositions, well, your largest number would seem to be bubbling its way up to the top, or equivalently, the smallest ones down to the bottom. So the bubble sort is kind of a formal name for that algorithm. We've just tried the first one with the cups. Okay, so just to explain myself a bit more algorithmically, much more succinctly, if you will, let me propose then that this is pseudocode. Again, we talked about this last week. In fact, there's no one way of describing any algorithm, but this is one such a way with a few English words here that I could come up with in as kind of small as possible and still be pretty precise with what I'm trying to say. So again, what we're saying is repeat until there are no swaps. Okay, the following, basically, for I from 0 to n minus n, if the ith and the ith plus 1 elements are out of order, then you need to swap them. Now, why this lingo? Again, computational thinking is about expressing yourself and thinking about yourself very methodically, very clearly, very ultimately, you're trying to define, say, some variables or some terms that you'll need in your arguments. And what I've done there is I've adopted a convention. I'm using I to represent an integer, some kind of counter, a number, if you will. And I'm using that to represent the index of each of my cups or of my doors, of my pages. And so again, if I'm adopting this convention of I, starting again, counting from 0 and working upwards to 3, 4, 5. And if I want to start looking at the first cup, aka 0, what's under the cup 1, what's in index 0, up to the n minus 2 cup, because again, if my first cup is going to be 0, and this is then 1, 2, 3, 4, 5, 6, 7, indeed the cup labeled 8, but it's actually in position 7, we can shift it 1 back. So in this position, more generally, if there are n cups, it would be n minus 1, because kind of bubble sorting is telling me to start at 0, and then look up to n minus 2, because in the next line of code, I supposedly want to compare the ith element and the ith plus 1 element, so to speak. Now, I don't want to look all the way to the end because, I actually want to look one shy to the end because I know I'm working now in pairs. I'm looking at this one as well as the one to the right, aka I plus 1. Okay? So effectively, the algorithm is saying it's like as you repeat this process again and again and again until there are more no swaps left, because like I proposed, you're swapping any 2 cups with respect to each other that are out of order. And so this is an example too of just generally smalling local problems and achieving ultimately global results. Because with each swap of those cups, I'm improving the quality of my data. Each swap in and of itself doesn't necessarily involve the whole picture, but if you put it together and we aggregate those smaller solutions, we've assembled then the final result and we've sorted our data. Now, I used two algorithms to show you. The second one here, if we go about this one, where again, I sort of started with some random cups, and then this time I selected one at a time. I actually wanted it in its place. At first I said, well, let's go and find the smallest number. Let's go and find the smallest number. And I found that out to be number 1. And then I put that way over there to the left. And then what I did after that is I found the next smallest number, which again, after checking my remaining cups, I determined it was 2. So I picked up number 2 and then I put that in the second place. And again, repeated that process again and again, not necessarily knowing in advance from anyone what numbers I'd find. But again, I went ahead and I checked every single remaining cup. And I was able to conclusively safely say that I had found the next smallest element in my array. And again, that algorithm has the same sort of name. It has a selection sort. I might describe this again in pseudocode in structure, but with a bit more different logic ultimately. So let me propose that what we do for I from 0 to n minus 1, where again, n is the number of cups, and 0 is by convention my first cup in an array, and n minus 1 therefore is my last one in the array. And what I want to do then is I want to take the smallest elements between the ith element and the nth element, at n minus 1. That is, find the smallest elements between wherever you've begun and the very last element, n minus 1. And then if, when you found that smallest element, you then swap it with the ith element. And that's why I was picking up one cup at a time and kind of swapping them in place, basically evicting one and putting another one where it belongs. And so once you start to do this again and again, because each time you're incrementing one, and whereas the first iteration of the loop, we're going to start kind of all the way there, and then the second iteration will start all the way there, the third iteration will start all the way here, and then so kind of the amount of problem to be solved is steadily decreasing until we only really have the 1 and the 0 cups left. We end up with just the final 2. So again, it took again some work for us to sort those n cups, but how much work did it take then? In the case of the bubble sort, remember the first algorithm we looked at, again, what I was doing is actually passing through each of those cups. Well, I was comparing, and then potentially I was swapping out each adjacent pair of cups, and I was repeating myself again and again and again. Well, if I have here, so n cups, how many pairs can you create? How many pairs of cups can you make when you consider swapping? Well, if I have n cups, I can say to make 2, 3, 4, 5, 6, 7, 8 different pairs at a time. So more generally, n minus 1. So in each passer, it would seem that I'm comparing n minus 1 cups. Now, how many passes would I ultimately need to take? It would seem to be roughly n, because in the worst case, those 2 cups might be completely out of order, which is to say that I indeed might do n minus 1 times. And if you multiply that out, I'm going to get some form of factor n squared. But then what about that selection sort? The second algorithm again, where I looked through all of those cups and I was trying to find the smallest cup and then repeating that same process from what's the smallest still. Well, in that case, I started with n cups and I might need to look at all of them again. And then once I found that, I might be able to find n minus 1. So there too, I seem to be running something like n minus 1 plus 1 plus minus 2 and so forth, So let's see if we can just summarize this as well. Just put this into, okay, let me propose mathematical line. Just to say that the first one with select sort, what we've done is this, okay? I'm looking for the smallest cup. I had to make n minus 1 comparisons because as I identified the smallest cup I'd yet seen, it was the smallest cup I could find. And then I compared that to no more than n minus others. Now, the first selection of the cup took me n minus 1 steps, but then it's done. The next selection of the next smallest cup would have taken me roughly only n minus 2 steps. And if you can see that logic with each pass, again, you'd have to do a bit less work until you eventually just left with that very last cup at the end, such as 8. So what does that actually turn out to? What does it sum to? Well, you might not remember this or see this at first glance, but it turns out, particularly if you look at one of those charts way back from the textbook, is that does this summation of series actually start to aggregate to n times n minus 1 is all divided by 2. Okay, now you can perhaps multiply this out to be a bit more readily as n squared minus n divided by 2. And if you factor that out still, we can get n squared divided by 2 minus n divided by 2. Now, which of these terms, n squared divided by 2 or n divided by 2, tends to dominate the other one? That is to say, like as n starts to get larger and larger and larger, which of those expressions has the biggest effect on the number of steps? Well, surely it's going to be n squared, albeit divided by 2, because as n gets larger and larger, n squared is still certainly as large as n. And so what a computer scientist will typically do here is just ignore those lower order terms, so to speak, and then they would just figuratively say with, just ignore them to say that this is on the order of n squared, this algorithm. Now, that isn't to say it's precisely this many steps, but rather as n gets really, really large, it's pretty much that n squared term that gets them, this matters the most. Now, this is not a form of proof, again, but rather a proof by example, if you will. But let's see if I can't come into again with a simple example numerically to that impact of the square. And just for those folks that join me a little bit later, I'm going to send over a handout to accompany what I'm talking about, just to make this a little bit easier on the eyes, should you want to have that in mind. So just put that again in the chat. Should appear somewhat cryptically in the, there you go. Perfect. I think that's it. Okay. So if I can show you an example, okay, just to show you that impact of the square, let's see if we can start again with that n squared over 2 minus n squared over 2 minus n over 2 and say that n itself, n is maybe like 1 million. So initially, so again, not 8 cups or 8 doors or whatever, not 1,000, whatever, but rather 1 million numbers, because I'm going to start to think in more realistic terms now, or bytes or any other element itself. So what does it actually sum up to? Again, so 1 million divided by 2 minus 1 million divided by 2, well, that happens to be 500 billion minus 500,000, which of course is going to give me 499,999,500,000. Now, I dare say that that's pretty close to big O of n squared. Why? Again, because if we say we started with 1 trillion and we halved it and then we ended up with 499 billion, that's still pretty close. In real terms, that's not nearly as equal the number of steps, but it just gives us a general sense of it's on the order of this many steps, because if we plugged into a larger and a larger values for n, billions, trillions, gazillions, that difference wouldn't even be nearly as extreme, okay? So let me show you this. Why don't we have a look now at these algorithms a bit more concretely into a better way altogether. Okay, so without the physical limitation of me poorly explaining this to you and the computer not being able to show you properly, I'm going to show you this picture, if you will. What I've found here is a website that has an array of numbers, but I'm going to picture these more graphically, wherein we have a couple of vertical bars, and the taller the bar, the bigger the number it represents. Let's see if I can zoom in further. Okay, so the bigger the number, the taller the bar. Okay, that kind of figures. So big bar is a big number, small bar is a small number. But they're clearly, like right now, as you can see, they're unsorted. Via these number of algorithms which we've already seen, bubble sort, randomize, this and that, what does this actually look like to sort my elements? So let's have a look. When I, if I zoom out further, yeah, let's just go here. So if I try bubble sort first, again, and this tool where I've gone for the first algorithm we talked about too, which shall be, let's say, a bubble sort. And you see rather slowly what we're doing is we're comparing pairs, looking at our elements from left to right and, only swapping them if they're out of order, swapping them again and again and again. Now, to be fair, like this quickly gets a bit tedious. So let me increase the animation speed all the way up there. There you go. So as you can rather see, we're sort of bubbling up of the largest elements and then we're swapping pairwise, only if they're out of order, swapping them again and again. Yeah. So previously it was I can't remember what was left, but now I have like 17, 18, 5 still got to go. 5 now bubbling its way to the left. There you go. 5 now's there. And now, okay, so we have 99, 97, 95. Indeed, those tallest bars are making their way up and the smallest bars are making their way down. We're kind of bubbling its way up. All right. Still going to take some time. And this is perhaps, an indication of the work to be done and the effort involved. But let's see if we can turn our attention to the other algorithm that I've got. So if I pause this one, in fact, if I duplicate that one, no, let's pause it. And I'll clean up. I don't really know how to clean. I'll just reload the page. So I want to try the second algorithm and I can randomize as much as I want to. If we'll try the selection sort, again, so that was the second algorithm we looked at again with the cups, to see if it perhaps looks a little bit differently. So here we have a selection sort each time, because each time what we're going to go through is the entire list. And every time we're looking for the smallest possible elements, 22, 22, 22, okay? So for a second, for the briefest moment, you can just see 31's highlighted in red, now 40's highlighted in red, because we have not until yet, there we go, we found a smaller decimal still, now 52 and 55, and we'll continue looking all the way through the rest of the numbers, okay, from middle to right, middle to right, middle to right, middle to right, just to be sure that we don't find anything smaller to the right, and once we do, again, we put that into its place. Whew. That was that. I'll just repeat that one more time, a little bit slow so you can appreciate what's going on. So I'll just repeat the process, randomize as much as I want to, selection sort. All right, so I'm kind of proverbially keeping the smallest number I've found so far in mind, 31. Oh, 26 is smaller. Now 6 is smaller. I'm going to keep that in memory until we go through them. I'm just going to, yeah, it definitely is quicker. It definitely feels like less effort involved, even if I did turn the animation speed all the way up, but still so. 4 is the smallest. 3 is probably the smallest. I'm going to use that one and then all the way to the left, making my way forward again. So we just repeat that process one more time. But Chantal's right, like definitely fewer steps now, because whereas there were n total bars, we don't need to look at the leftmost now because that's kind of sorted, okay? Whatever I've got there, these bars are now done. I can disattend from them. So if I just speed them up a little bit more. So now we only need to look at n minus 1. Okay, n minus 1 again. I've got minus 3, minus 4 again, because each time I'm kind of reducing the element in my array. So the process will start each and every time again. We found 10. Okay, good. So the fact that we're just double checking that there's not anything smaller off to the right gets smaller and smaller. And now I got 13 in its place. Now, of course, we as humans, we have the advantage of us being human. We have more of an aerial view and, of people of this data, we can kind of make out what's what. And something like a computer could remember just the smallest number that it's recently seen. Why not for efficiency's sake remember the 2 smallest numbers or the 3 smallest numbers or the 4 smallest numbers? Like that's fine. But the argument is that it's, quickly devolving into just remember all the original numbers. So yes, like so perhaps you could save some time, but it sounds like you're asking for more and more space with which to remember the answers to those questions. Now, this too, again, would seem to be taking all day. Even if down here we increase the animation speed, it is still selecting those numbers a bit faster. But again, there's still so much work to be done. Indeed, like these 2 comparison-based sorts, so like comparing things again and again, and then redoing that work in order to improve that problem, just to end up, on the order of, bingo, n squared. There you go. So, which is to say that n squared or something quadratic tends to be rather slow. And this is, again, in quite contrast to our logarithmic time, divide and conquer. But that logarithm thus far was searching, okay? What we're doing here is we're actually sorting, different kind of algorithm. So let's compare the 2 numbers side by side. Another website I found. This is another cool place where, albeit with different tools though this time, and this presents the information a bit more graphically, a bit more sideways, if you will. Just to zoom in, there's a few more algorithms we've not looked at tonight, but let's focus on ones we do know, okay? Again, so what we have are bars, and the bar is going to be the small, the small bar is a small number, big bar is a big number. We can imagine that as being kind of size indicative. But again, what we've done is we simply rotated it 90 degrees. So previously this was going up to down. This time we're just going to go facing rightwards. Whatever, that's a stylistic choice. But on the left we have sort of selection sorts. And what I'm going to do is I'm going to choose these 2. I'm going to get my pen. So let's just focus on ones we've talked about thus far, which are my bubble sort and my selection sort. All right, so both whose bars seem to be randomly sorted so that neither has an edge necessarily over the other one, as you can see. Okay, let's just go ahead and play all of them. Well, let me just play these 2 for now, just to see what happens there before we go through all of them. There you go. But okay, I gave a millisecond advantage to selection, but let's see indeed how that happens. And already you can kind of tell that bubbles seem to be bubbling its way up, and selection is improving its selections on the go. Can you see how that happens? So bubble would seem to win here, but only because selection has a bit more work to be done. Bubble happens to, even if I do select selection first, bubble will usually finish first. But again, there too, it's pretty close to the tie. One more time, and it's done. Well, can we do better? It turns out we can. Like, so long as we use a bit more of that intuition we had when we started to think about things computationally, when we try to divide and conquer, try to divide and conquer. In other words, why not? Given that we have n doors or n cups or n pages or n elements, why don't we divide and conquer that problem again and again? In other words, in the context of the cups, why don't I simply just sort for you the left half and then the right half, and then with the sorted halves, just interweave them for you together. Now, that would seem to be a little bit different from just walking back and forth, swapping the elements, again and again. Just do a little bit more work for yourself here, and a little bit more now, and then just reassemble your total work. Now, of course, like if I simply say, I'll sort this left half, and I'll sort that left half. Like, what does that sort of mean, half? Well, if I say this left half, let's imagine this like this. I'm gonna sort the left half, and then on the right is gonna be the right half. I'm just gonna use colors again, not drawn to scale, and then I'm gonna sort them out within each other. So green is now sorted from smallest to biggest. Same goes for blue, and then I'm just gonna interweave them back for you together, which simply means that thereby, like, we're just making the problem smaller. Somehow or other, we could use that intuition of the binary search, but we were applying it to sorting this time, to sorting algorithms. It's not gonna be quite in the end of, it's not gonna be quite as fast as the binary search because, at least with sorting algorithms, as we see here, you sort of have to deal with all of the elements. When we're sorting, we can't simply just tear off half the problem away because, you're going to be leaving half your elements unsorted. The whole goal is for us to put them in order. But it turns out that there are a whole bunch of other algorithms that are faster than selection or faster than bubble sorts. And, amongst them, one of those is called merge sorts. So merge sorts kind of uses exactly that intuition of dividing the problem in half and then half and then half. And to be fair, like touching all those halves ultimately, but doing it so in such a way that feels much more efficient and uses less comparison-based sorting than, say, bubble sort or selection sort would themselves. So let me go ahead and just play all three this time. Focusing on, I'll just play all of them, but you can kind of focus on the ones and see which one wins now. So merge, bubble, and selection. Yeah, clearly. So after a moment, I think there's nothing to say, right? I'll even let you choose selection, bubble, merge, just these three alone. And merge has already won. Like, it's so much quicker. There you go. Even though, bubble has, then finish, and then now selection has as well, merge just seems to work through that list a lot quicker. Perhaps this was a fluke. Again, just to be fair, these numbers are random, but merge maybe sort of got lucky. I'll play the test one more time. Play all. And, it's going to win every single time. The pattern actually does change if you look at the page, if I refresh it again. If you can kind of see the actual halving again. So that seems then half of the list gets sorted, and then you're going to reassemble it at the very end. Okay, and then so you can, before we do go for a little bit of a break, let's just zoom in on that algorithm, specifically this one of merge sort, just to understand it one more time. Okay, so we have merge sort, and again highlighted in colors. We sort of do work exactly the elements that you're sorting again and again and again. The reason that so few of the bars are being looked at once at a time is because logically or recursively, if you will, are we still sorting the first half? No, but the left half of the left half. Let me just turn that down somewhat. So the left half of the left half, but then the left half of the left half of the left half, and so forth. And this really just boils down to kind of ultimately is sorting individually, individual elements, basically. But if I hand you one element and say, take this and sort this, it has no halves. So your work is your work is done. You don't need to do a thing. But then you do have these two other halves, each of size 1. There might be indeed some work to be done there because this one is smaller than the other one, or one is larger than the other one. So you do yourself need to interleave those two for me to merge them in. And that's exactly what merge is kind of doing here. It's going to just increase animation speed, as you see as we go. Like half of the list is getting sorted at a time. It's not perfect and it's definitely not smooth, but because that's half of the other elements are there, but now re-emerging of the other halves. And that was really fast. It is going to finish a lot quicker than it would have been for me to do bubble sorts or selection sorts. But again, there was a price being paid. Now I'm doing the second half. Can you see? Only working half and half, and then finally interleaving the sorted sets. So if you think back to our vertical virtualization of bubble sort here for a second and selection sorts, but this time we're kind of re-merging those two halves. This is going to finish a lot quicker. Indeed, that would have been the case for those bubble and selection sorts as well. There you go. All right. So they were doing all that work kind of in place. Merge sort seems to be getting a little bit greedier on us, if you will. Like it was temporarily putting some of those bars down there, effectively like, using twice as much space for those first two algorithms because it's kind of doing two things at once, two juggling act, comparing it to, say, selection or bubble. And that's where merge sort gets its edge fundamentally. It's not just a better algorithm per se, but it's a better thought out. It's better. It actually consumes much more resources. Not time, not space, but just by using twice as much space. Not just the top half of the screen, but the bottom half as well. And then you can sort of merge them temporarily and put some of its work over there, and then continue doing some of its work over there, and then just reassemble them and stitch them back together, merge them at the end, if you will. Okay. So both selection sort and bubble sort did have that kind of advantage. They had to do everything in place, and that's why we had to then swap out so many things at a time. So many times, we have fewer spots in which we had to work on in that table. We're sort of doing pairwise, one at a time, or finding the smallest element and working upwards. But at least with merge sorts, merge sort tends to occupy a little bit more space, a little bit more time, a bit more space, a bit more memory, and then you can reduce that amount of time. Which is to say that there is a relationship again to time and space. And I think that's when we're going to talk about memory when we come back. Looking at the time, it's just gone half at 9. So why don't we give it a 10-minute break and we'll look at how maybe algorithms look inside a computer. I hope that's making sense so far. Again, I'm just going to put the timer on just to give you a chance to get a cuppa, and we'll be back in a few. I'll send over that link one more time just for good measure.
Marco.
Hey, how's it going, Dennis?
Yeah, got a question. mean, I've been attending most of your sessions. I'm just wondering, like, I mean, a lot of us here, well, I speak for myself, we're not, obviously we're interested in AI. So some of your stuff comes across as really advanced, right? So I know it's relevant, but I mean, how is this something we get to use later on in our AI journey, maybe in a few years' time? Or is this, you understand what I mean? Is this something we need to learn now?
Well, what I'm doing here is I'm peppering in this way of thinking algorithmically. The topic today was kind of data structures, which if you started to look into AI and I think as an engineer would, a lot of what a machine learning engineer does is evaluate these models. And if you look at SageMaker, that's all that the product really is. It's just testing and performing SageMaker models. So you can spend, if you have to have some analysis onto this, and you need to think computationally, but perhaps also kind of express yourself computationally and trusting that the computer can do that bidding that you now pass in. Okay, how the data itself is really going to be organized in a blockchain. How is what's the secret source that those languages, that those tools, whether that's for chatbots or some other use case entirely, all of them indeed, when you look underneath them, they do seem to have this backend system too. Kind of the intellectual property that underlies all those systems ultimately boils down to not only the algorithms in use, but also the data structures also, because together, like vectors and data structures too, they combine to produce not only the correctness of the answer that you want, but also the efficiency by which you can then access those answers and find them. So we're trying to disambiguate here is which data structures or which algorithms perhaps work better. Just a fundamental, a baseline awareness of them is going to be helpful in place. But you're right, this does feel like it's a little bit out of touch. Remember that this is just...
No, it's interesting. I just need to try and figure out where at some point we're going to apply this knowledge. Because obviously, with the AWS environment, you more or less a lot of click and, a lot of clicking, whereas you have some other AI environment where you have to get your hands dirty, go in the back end, you write codes, Python, script, all that stuff. So I'm just wondering where we get to apply this, or
It probably wouldn't be, so I'm not sure if you are taking a machine learning course, but the one that I found very helpful was a Udemy package that I got a little bit of trying, I did sample, I tried to do a little bit of machine learning stuff myself. It is exorbitantly expensive to train a model from scratch. If you had millions of pounds, you're willing to throw them at something, you can arrive at the same conclusions that other more established people have got to. I don't really see a use case for doing this, but perhaps from our point of view of fine-tuning a model, it is all the more worthwhile to know how to think about these algorithms and also trusting the data structures on which they underlie them. We're trying to, and I'm not sure if you are studying this, but you will, or your teacher should teach you about evaluation. How do you evaluate a model? There are many ways of evaluating a model. Is that something that you have done or seen already?
I don't recall learning that from Sunita at all. Unless I was falling asleep, but I can't remember any session about evaluating a model. But yeah, but it's good. Cool. I could look into it. I guess we all can. Right. Well, I'll let you go on your lunch or your break.
That's fine. I'm fine with that too. I'm definitely so impressed. If you're on these lessons, make the most of them. I'm surprised that she didn't talk about. So the whole purpose of machine learning in SageMaker Studio is to look at the models. It's not to just have them, is to kind of fine tune them. So you absolutely do need to know a little bit about algorithms and data structures in order to work with machine learning at the very minimum. So I would definitely press that and say, how do we evaluate things like ReLU, TensorFlow, all the. There are many. It's a big discussion, of course, but evaluating machine learning models can be done in the studio, which you have to look at the correctness of your answer and put them into a grid of sorts. And it's kind of slipping me. Like I actually took the exam and I forgot all the terms now. But just be familiar that this is perhaps too much for Solids to kind of cover in one go, and there is a lot of
that is true. Yes, it's quite a lot of stuff, right? Yeah.
Where we have experiments is one thing. So they've changed the interface one more time. But all this idea of evaluating and fine-tuning the model has to come down to the algorithms in use, but also the data structures in use within them. So when we come back, I'm going to get a cup of coffee, and when we come back, we can talk about how we can see this in the context of a linked list, which is maybe a bit more familiar with you. Yeah, let's come back to it. And I just, it is fine time. I just wanted to explain as well, just thinking about Dennis's question, like why are we here? What are we talking about? I'm also planning on doing next week's session on the blockchain and how we arrive at, Bitcoin, which is huge, in today's news. Bitcoin, for those I don't know, is going to the moon. And it seems to be that everyone is getting very frenzied with today's news. And so it's all very exciting. And underlying all of this is a blockchain technology via which I want to explain to you in next week. Okay, but just before we get to Bitcoin, it's worth us understanding a little bit how data is itself going to be structured and how we can then interpolate data. Okay, if you will. But just before we get there, what we've been so let's come back. Okay, the discussion so far has been about evaluating types of algorithms. I've shown you 3 so far. Well, 4, including binary. So search sort, bubble sorts, binary sorts, and selection sorts. Now, all of those algorithms, they do assume that our data is going to be back to back to back. That is, we said stored in what we call an array. And that's great because that's exactly how a computer is so inclined to store data inherently. That's how it works. For example, what you might find inside your phone, your device more generally, is this thing here. It's called a stick of memory or a stick of RAM. RAM is short for random access memory. Indeed, albeit a bit of a misnomer, like the R in RAM, random, it actually means that the computer can jump in an instant, shall we say, or in constant time to a specific byte. That's what I mean by, it can pick a book off the shelf in constant time. That's very, very important when you want to jump around our data, our cups, our pages, our doors, in order to get that data instantly, if you will. And the way that actually works is, so if I click on here, you can see the reason that it's so conductive again to laying out that information back to back to back continuously in memory is if we consider what's inside the stick of RAM is this black chip here on the so-called DIMM. DIMM, so that's the dual inline memory module, in which we have this kind of obstructed black chip, really, if you will, like an artist rendition at hand. So if I zoom in somewhat again, this proposes that if you have some number of bytes in this chip, say 1 billion for 1 gigabyte, okay, or 1 million for a megabyte, it stands to reason then that we humans, we could, again, number those bytes from say up from 0 all the way to 1 billion. If I was storing 1 gigabyte of memory, shall we say? I know today's computers are much more powerful. So 0, 1, 2, 3, 4, 5, 6, 7, kind of roughly speaking, going all the way up to 1 billion. So top number 1 is going to be 0, next one might be 1, and then thereafter should be 2 and 3, 4, 5. We can reach any and every one of those bytes. And so when you store a number on a cup or behind a door, that amounts to just writing those numbers in each of those boxes, if you will. Okay. And so each is next to one another. So with a little bit of simple arithmetic here, a bit of dividing, a bit of rounding, you might then be able to just jump instantly to any number of other addresses. There is no moving parts to round. There's no moving work to be done here. Just like your human hands would have to do if you're kind of moving cups about, if you're going from here to there, with your feet, in the real world. This is why computers work in constant time. Rather, the computer in RAM can instantly jump to that so-called address or the index of the array. You can just get there straight away. Now, what we can do here is when we have a canvas that allows us to remember in this sort of way in an array, is we can represent any number of types. Indeed, like as in Python, just there are sorts of other types of data, and these are a few. For instance, these might ring true for some of us. Like for example, a bool instead what we call a Boolean value, and a float again for a floating point value, a real number again with a decimal, an int again for an integer, a string for a string, and each of those is laid out in memory in some particular way that's then conducted to for a computer to be able to access it more efficiently. The data type is what allows that information to be retrieved, because that's, again, back to this, precisely why too, if you've studied databases, when you run into issues when storing or using something like a float, perhaps because if you decide a priori to only use so many bytes, bytes to the left and to the right, and above that and below that, it might end up getting used by other parts of the program. And so that if you only ask for, say, let's say I've only asked for 32 or 64 bytes or 4 bytes or 8 bytes, because you're then going to be surrounded by other data, that floating point value, or really some of the value, can only be so precise, let's say, yeah? Because ultimately, yeah, we're operating in bits, but those bits, those binary digits, are physically laid out in some kind of an order on a machine. So your DIMM, your dual inline memory module, basically just a small circuit here that holds your memory chips together. Each of those back chips here, this contains obviously billions nowadays of tiny little store cells called capacitors, and those hold bits of data as electrical charges. Inside those chips, if you build them up, you'll have capacitors which are arranged in rows and columns like this, and they form a grid, but we're going to call these things an array, and each spot in that array corresponds to a unique address. So our computer is able to then pinpoint exactly where each piece of data should live. So when the CPU says, I want some data, gobble, 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 it sends an address over to the DIMM, and then it quickly locates the right chip, the right cell within that grid to read or write the data to and from. Because then, for us, all those cells are going to be lined up in order continuously. The DIMM hands it over in contiguous chunks. It's like reading a row of books on a shelf. That makes accessing nearby data a lot faster. And I'm going to prove it to you. Okay? So, with that said, what are the options, again, that we can paint to the canvas? Surely it'd be nice then for us to have a way to store data that's not necessarily always back to back to back in this way, but also we can create a more sophisticated data structure, like we've seen these already. So as to not support these types only, but also ones like these as well. So we've seen the likes of a dict in Python for a dictionary, otherwise known as like a hash table too. A list as well for a sort of an array that can grow, it can shrink, and a range as well for a range of values. A set for a collection of values that contain no duplicates. You can't have two things the same. And tuples as well. Tuples being something like x, y, or latitude, longitude, and so on. These concepts. I mean, surely it would be nicer for us to have accessible to us in a higher level context like Python. But at the end of the day, if we're trying to do something with machine learning or AI generally, is we have at the bottom just bytes of memory back to back. We need some layers of abstraction upon that memory, so as to then implement these more and more sophisticated structures to work with them. So let's have a look at a few in particular. I'm going to look for now for instance true from the previous slide, as well as dict and list here, again, because all these somehow need to be built up on top of those lower level principles that we're looking at today of memory. So how might that work for us? What problems might that solve for us? And what I'm going to do is I'm going to use my board as a canvas, and I've drawn this ahead in advance, like on PowerPoint. I've drawn that same grid of rows and columns on my DIMM in order to divide this screen into a bunch of bytes. So again, I've done this with PowerPoint. I've divided my board into a bunch of squares. Each of these squares represents an individual byte, and each of these bytes, again, a binary digit, 8 of which has some number that's associated with it, some value therein. Now, the number is not the number inside the box per se, but the number is not going to be the bits that compose this, but really just the metadata. And this is an index where the address in that index that exists implicitly, but it's not actually stored, okay? So this is kind of what I'm associating as the metadata. If you can see through what I'm telling you is this might be index 0 or address 0. This might be index 1, address 1, 2, 3, 4, and 5. Again, this is just for artistic sakes. This is not actually stored anywhere. Move to the next row, and then we'll call this one 6 and 7, 8, and so forth. So we have an array. Suppose then that I want to store some actual values in this memory. So in your DIMM, the way that you kind of load a program is to go ahead and just do that, to put some values in memory. So then we might do something like this. We might actually store the number 4 here, followed by the 8, followed by the 15, and the 16, perhaps followed by the 23, and then the 42. And so we have some bunch of random numbers inside of this too. Okay, just because those numbers are back to back to back to back, we can call this an array of size 6. Because we said the first index is address 0, the last index is address 5, and so in between then we have a total of 6 values in our array. Now, what can we do then if we're then ready to add a 7th number to this list? Well, we could definitely look down here and maybe put that into this spot there, and because this is the next appropriate location, sure. But that depends on whether or not that spot is actually available. Because the way that the computer typically works is that when you're writing a program, you need to decide in advance like how much memory you want to load, and then you tell the machine via your operating system, be it Windows, Mac OS, or Linux, or whatever it is. Just your operating system is telling how many bytes of memory you would like to allocate to your particular problem. How much memory am I going to occupy? And so, if I only had the foresight to say, well, I would only like these 6 bytes in which to store 6 numbers, like Windows or the operating system might have handed me that back and said, fine, there you go, have 6 bytes. But the operating system, thereafter might have proceeded to allocate subsequent adjacent bytes, like 6 and 7, so on, just to some other aspects of the program. Which is, again, to say that you might have painted yourself into a bit of a corner here by only in code asking the operating system for those initial 6 bytes. You might instead have wanted to ask for more bytes so as to allow yourself this room to grow, but you didn't do that in code. Obviously, you might just be unlucky. So that's the price that you might pay for an array. You have this wonderfully efficient idea, this way for you to search it and search it randomly, which is to say instantly via arithmetic. You just jump to the beginning or the end or even the middle, and then as we've seen, just perhaps by doing some addition, some subtraction, division, some rounding, that gets you ultimately right to where you want to go in some constant state in a very short amount of in a short spell and a few amount of steps. But unfortunately, because you wanted all that memory back to back, it's then up to you to decide how much of it do you actually want. And if the operating system says, okay, I'm sorry, like you've already allocated 6 and 7, it's already been used up elsewhere on the board, kind of someone standing there, then you might be faced with that particular, that decision, just as to say, no, I can't accept any more data. Or you might say, okay, operating system, what if I don't mind where I am in memory? You probably don't really care where it is, but I would like you to find me more bytes somewhere else. Those seats are occupied? Well, what isn't? So rather than like going from, from a 1-bedroom to a 2-bedroom apartment, so that you can have more room, you might physically have to pack your bags and you have to go somewhere else. Unfortunately, just like in the real world, that's not without a cost. You need to pack your bags, you need to physically move, you need to do all that work, which takes time. And so it would take your operating system some time, some effort to relocate every one of your values. And it might not even get it right. So sure, yeah, I mean, there might be plenty of space down below on, multiple rows or not even pictured down here. But it's going to take some amount, some non-zero amount of time, some work to relocate those, that 4, that 8, that 15, that 16, that 23, and 42 off to new locations. That would take some work for it to be done. Now, that might be your only option if, you want to support more data, and indeed, like most programs probably want to support more data. It'd be quite an unfortunate situation then if you had to tell your user or your boss, like, I'm sorry, I'm out of space in my memory. That's certainly quite silly if you actually do have more space down below, but it's just not right there next to you. So with an array, you do have the ability for you to physically perform very sophisticated, very efficient algorithms, as we've seen, binary search, bubble search, selection sort, merge sort as well. And so in quite a fast amount of time, even though selection sort and bubble sort were kind of big O of n squared, merge sort was actually n times log n, which is very slow, which is slower than log n alone, but faster than n squared. They all presuppose then that you have some random access to elements algorithmically, via those indexes, via an address. And so do you too then, like, so, from a computer's memory point of view, from an array's perspective, you still need to commit to some value. Okay, so fine, let's change that idea. Let's not ask the operating system for 6 bytes initially. Let's say, give me 7, because I'm going to leave one of them blank. Now, of course, I'm going to say, give me 7, including this one as well. That might buy me some runway, so to speak, that I can accommodate if and when I need that 7th element. But what about the 8th? Yeah? Well, you could ask the operating system from the get-go, say, okay, well, don't give me 6 bytes of space, but give me 8, or give me 16, or give me 100, whatever. But at that point, you're kind of getting a little bit greedy, and you're starting to ask ahead of time for more and more memory than you might actually need anytime soon. And that too is unfortunate because you're just being wasteful at that point. Your computer, of course, this little box, it only has a finite amount of space. It only has a finite amount of memory. And so if you're asking for it, more and more of it that you actually have or need, that memory, by definition, is going to be unavailable to other parts of your program and perhaps even others as well. So your computer ultimately is not going to be able to get as much work done because it's been holding off to the side just some empty space for you to maybe use, okay? Empty parking spaces that you've reserved for yourself or empty seats at the table that might potentially go unused. It's just wasteful. It doesn't seem right. And hardware ultimately costs money, and hardware lets you solve problems, and money lets you solve problems. So if you've got less and less hardware available, can you solve your problems at hand? So it doesn't feel like a perfect solution, okay? Again, there are a series of trade-offs here. It depends on what's most important to you and what are you doing, what are you trying to accomplish with data, like time, space, or money, or development, or any number of other scarce resources. So what can we do instead of an array? So how do I go about, what I'm trying to introduce here is getting some dynamism, getting some dynamism that I clearly need here, that I want, whereas it wouldn't be nice if you could just grow these great data structures, and better yet, like even shrink them, grow them and shrink them. If I no longer need some of those numbers, perhaps, I'm going to give you back or reallocate that memory so that I can use it elsewhere for more compelling purposes. That's what I'm trying to do here. It turns out that in computer science and machine learning more generally, programmers can create very, very fancy data structures, but at a high level of abstraction. You won't see it, like in the console's not going to show this to you, which is why I'm telling you that it turns out that we can actually start to make lists of the values. Like if I actually wanted to add some more numbers to my screen, here, for example, and maybe, so let's imagine that maybe those 2 spots are going to be blocked off for something else. Yeah, I've said these seats are occupied by another program, perhaps. And for instance, these 2 spots are stopping my, rather than using an array now, you know what, like I do know that there is some room kind of elsewhere on the screen. It just so happens to be kind of available elsewhere. Here, for example. And you know what? So if I want to put the number 50, the number I was looking for, in my list of values, I might have to say, you know what? I don't care where you put it in randomly for as long as I care. Just go and put it there. I'm going to put it into that random place. Well, what is there? Again, if we continue this indexing, this is going to be 6, that's going to be 7, 9, 10, 11, 12, 13, 14. Well, 15, okay? So 50, it just happens to end up, by chance, by coincidence, at location 15. Because maybe it's the first byte available because, not only because of these 2, but maybe all these other ones are also taken up for some other reason. Some of the program might be loaded up in memory. Ever since you asked for your first 6, that's okay. You asked for 6. So long as we can link my original data to the new data, that's fine. So if it's already here, I might just be inclined to say, you know what? Let me just leave a little breadcrumb, so to speak. I want to leave something that reminds me to say that after the 42, I should actually, follow the breadcrumb and follow the arrow, sort of shoots and ladders, if you will, and then go down to index 15. That's fine. Like if you can do that, after all, at the end of the day, computers will do what you want. Okay, so if you can write the code, if your operating system can implement this idea, this metadata, in fact, it will remember that value for you. But how do you achieve this? Like here, we have to come back to the fundamental definition of what your computer is doing and how it's doing that. Like it's got that chip of memory. Remember that those bytes back to back to back, and kind of picture there. So this is all you get. You know, there is no arrow feature inside of the computer. You have to implement that notion yourself. So how do we go about by doing this? How do we get that breadcrumb? Well, we can implement this concept now of an arrow, but you need to implement it ultimately at a lower level still, or just trust that someone else will do that for you. Your operating system will do that for you. As best as I can tell, I do know that my first several elements, 4, 8, 15, 16, 23, they seem to be back to back to back to back from 4 all the way up to 42 in locations 0 all the way to 5. And because those are contiguous, I get my random access and I can immediately then jump from the very beginning to the middle to the end. This 50 and kind of anything after that, that needs to be handled a little bit better. Like if I want to implement this kind of arrow, this space I've got between them, the only possible way seems for me to somehow remember the next element in after 42 is at location 15. So that location, aka the address, you know, the index, has to be something I remember. Now, unfortunately, I don't have quite enough room for me to remember that. What I really want to do is kind of not store the arrow, but by the way, like parenthetically, go ahead and store the number 15, you know, not as the index of the cell, but at the next address that should be followed. The catch, though, is that, you know, I've not really left myself enough room. I've got to make this this mental model in parentheses that we've got to solve this little problem a little bit better now, perhaps. So let's just start over for the moment, just to go back. I don't need to worry about this low level stuff again because at some point it's just going to get too messy. It's not that interesting for us. It's like talking in zeros and ones. You know, I don't want to talk to you in bytes in this way, but let's try to go up the chain, up the abstraction ladder, if you will. Just agree then that somehow you and I are able to store values in memory. And those values can be data. Those numbers can be numbers like 4, 8, 15, 16, all the way up to 42 and now 50. And so we can now also store somehow the addresses of the indexes, the locations of those same values. It's just up to you and me now how we decide to use this canvas. So let's go ahead and actually clear the screen now. Let's try to build up a high level concept of this, not an array, but something a little bit different, which we're going to call a linked list. Now, what's a linked list? So a linked list is going to be a data structure that's a little bit higher up the conceptual ladder in the abstraction of this sense. Sorry, data structure. Ultimately, you know, these are just chunks of memories, chunks of bytes. But this linked list will allow me to store more and more and more values and even remove them simply by just linking them together. So let me go back ahead and just, what I'm going to do is I'm going to represent those same values again. So 4 followed by 8, followed by 15, and 23, and then ultimately, you know, 42. Eventually, what I'm going to want to do is store 50. But I've run out of room. Like my space is only so big, okay, which is fine. I'm going to go ahead and I'm going to write 50 wherever there's space, which could be down here in my array, in my RAM, okay? But I don't want to worry about grid and rows and columns in memory. Like I want to get out of that mind space. So let's just stipulate that, yes, there's actually, you know, they're actually there, but it's not useful to work at that level. Much like it's not useful to actually talk to you in zeros and ones, okay? So let me go ahead and actually wrap these values in a higher level idea. And we're going to call this thing a node, or just a box. Yeah, a node is just a helpful term of ours. And so this node of this box is really just going to store it's going to store a value for us. So here I have 4, here I have 8, 15, here I have 16, 23, finally 42. And then when it comes time to add 50 into the mix, that too will come in this box. What is this box? What is this node? Again, this is just my rendition, my drawing of the underlying bytes in your memory. But now I have the ability to draw a better, like a pretty picture, if you will, like somehow interlinks those boxes together. Indeed, what I ultimately want to come out of this is I want to remember that 4 comes before, you know, if this comes first, 42 comes last. But then wait, if I now have 50, this new value, this new element in my list, I'm going to say this now comes in last. So we could do this, you know, quite artistically, simply by way of those arrows. These arrows simply point each box to the next, implying then that the next element in the list is this one, and you should find it there. Whether that's next door or it's really far away, it just so happens to be the end of the arrow. Follow the rainbow, you're going to find the next element. What are those arrows? Like what? Again, these arrows are not something that you and I can really represent in a computer. Like, be at the end of the day, you have just blocks of memory. Inside of them are bytes. If all you have are bytes, when therefore like patterns of zeros and ones and zeros, wherever you store in the computer's memory must be representable by those ones and zeros. Amongst the easiest things that to represent, you know, we already know are numbers, like indexes or addresses by those nodes. So for instance, like depending on where those nodes are in memory, we simply just check that address and store it as well. So again, for instance, if the 4 just happens to be the address 0, and this time 8 is going to be at the address 4, this time, you know, this is 12, and then this one's 20, at some point, just by chance, back to back to back to back, these are 4 bytes apart, 32 bits, or 50 might be some distance away. Maybe I'm just going to say it's at location 100, and that's fine. You know, these are 4 bytes apart, but some kind of way over there, we can still do this. Because if we use a part of this node or this box to implement those actual arrows, where you can actually store that information we need to know and how to get from one box to the other. For instance, for me to get from 4 to the next element, you're going to want to coincidentally go not to number 4, but to address 4. And again, if you want to go from value 8 to the next value 15, you're going to want to go to address number 8. Again, if you want to go from 15 to 16, the next address is going to be 12, followed then by 16, followed then by 20. And then herein lies the magic, because if I want to go from 42 to the newest element, that's just somewhere else down below at address 100. That's what gets associated with 42's node. And, you know, as for 50, that's a dead end. You know, there's nothing more to do there. So we might simply just kind of draw a line in the box there, just saying, that's it. You know, store 0 bits or just some other convention like that. So there's so many numbers now on screen, but to be fair, like that's all that's going on inside of a computer, just storing those bytes. But now we can stipulate then and say, okay, well, I can now somehow store the location of each node in memory by using its index or using an address. It's just, frankly, not all that pleasant for us to stare at those values all day. Like, I'd rather just look at them and draw the arrows more graphically, thereby representing the same idea of those pointers, if you will, like a term of art in some languages that allows me to remember which element goes to which in a linked list. And so what's the upside of all this overhead we're now doing? Well, now that we have the ability to string together all those nodes, and frankly, like if we wanted to go and remove those elements from the list, that's fine. We can really just snip it out. We can simply just update where that arrow is pointing to. Equivalently, we can then update the next address in that node. And then we can certainly add to the list as well. After 50 comes what? We can draw more nodes over here, perhaps over there, and just simply link them together with arrows conceptually, or more specifically, by changing the dead end to an address of the next element. And so we can create the idea of the abstraction of a list using this canvas of memory. But no one is good here. Like, surely we've paid a price. Like, surely we couldn't just get dynamism for addition and the removal of updating a list without paying some kind of price. The way that we've introduced dynamism, making it more dynamic, this ability to store as many more elements that we want to without having to tell the operating system from the get-go up front how many elements we expect. Like, indeed, well, we may be lucky at first, perhaps, if we know from the get-go we need at least 6 values there. They might be a consistent distance apart, 4 bytes or 32 bits altogether. And so I could do the arithmetic on some of these nodes, but that is ultimately, unfortunately, no longer a guarantee of structure. Whereas arrays do guarantee you some random access, linked lists don't. A linked list would require that you traverse them in order to a linear time from the first element position all the way to the last. There is just no way for us to jump to the middle element of a linked list because, frankly, if I do the maths like before, 100 bytes away is the last, so 100 divided by 2 is 50, and then running down, giving me access to all the... that puts me somewhere over here, and that's just not right. That middle element, the one we saw earlier, is going to be like here, 15, 16. Because now there's no support for random access or for instant arithmetic access to the elements like the first, the middle, the last. And so let's remember now that for the linked list, at least now, is the first element, and then from there we have to follow all those breadcrumbs to get to where we want to go. So that might be too much of a high price to pay. Moreover, there's now overhead too involved because I'm not storing every node one value, but two. I'm storing the value in blue, the thing I care about, but also I'm storing the address, kind of the metadata that goes alongside with this that allows me to get to the next node. So I'm actually, just by definition, having two things to do, I'm using twice as much space. And there, at least when it comes to storing the numbers, but at least I'm getting some dynamic support for that growth. So again, these things depend on trade-offs and what is less costly for you. But never fear, this is just, again, another problem to solve. Just to be clear, what I like to do is I'm going to try to retain this idea of dynamism that a linked list can offer us. Again, this is the ability to grow and shrink even after the data structure over time without having to decide a priori just how much memory we want to allocate. But at the moment that we've lost the ability to search very quickly, as with something like binary search. So wouldn't it be nice now for us to have something that, if we've got both properties together, the ability for us to grow and shrink as well as to search fast? Well, I dare say that we can if we're just a bit more clever with how we draw our canvas. And again, just to stipulate now that we can certainly we can store values anywhere in memory in our DIM and somehow stitch them together using addresses. Now those addresses, otherwise known as pointers, we don't need to draw them anymore, again, because now it's just going to be a distraction. But suffice it to know that we can just draw them pictorially with some arrows. So let's just go ahead and do that. Okay, I'm just going to draw again these values as before. I'm going to draw my values, say 16 up top, followed by an 8 and a 15 and a 4, and over there I'm going to draw my 42 and my 23. And somehow it remains for me now to somehow link these things together. Since I don't need to leave room for those actual addresses, kind of got those out of the equation, it just suffices now to draw arrows. So then go ahead and just draw a box around 16 and 8 and 4 and 15 and so on. How should I go about by linking them? Well, let me propose then that we're no longer just linking from left to right, but actually assembling more of a hierarchy, maybe something like a tree. So maybe with 16 pointing down at 8, but also pointing down at 42, and 42 meanwhile pointing down to 23, 8 now pointing down to 14, to 4 to 15. Why have I done it this way? Again, because I've included those arrows, sometimes a bit bidirectionally here, like I stitched together a two-dimensional structure, if you will. Now, again, surely because this can be mapped to that lower level of memory just by jotting down the addresses of each of those arrows with respect to. But I like thinking at this level of abstraction because now it gets into much more of a sophisticated form about how I might lay out my data. So what properties do we get with this? Well, remember, so dynamism was my first goal at hand. I'm just going to pull up my PDF. So if I'm trying to remember... Oh, come on. There we go. So with my linked list, fortunately, I know that 42 has only got one arrow off it, but there is still room for more. How do I go about by adding more number into this? Say if I want to add 15 to this number, how do I get 50 and add this to my structure? Again, because if I look at the top here, like 16, so we've got 2 arrows off to the left, off to the right. I know it's full, but I do know that 50, if I'm looking for 50, is bigger than 16. So let's start to think about, that dynamicity and maybe say 50 shouldn't go down there. That's maybe wrong. 50, if I'm trying to look for 50, should perhaps fall in this side of the coin. It should perhaps go off to the right because I know it's bigger than 42. Sadly, though, because 42 has already got one arrow off of this, that's already one thing, but there's room for more. It turns out that 50 is bigger than 42, so you know what? What I'm going to do is I'm just going to go off and draw that to one side of it, draw a second arrow off to 50. Now, what picture seems to be emerging here is perhaps reminiscent like a family tree, if you're familiar, like with parents and children and tree more generally with roots, perhaps. Now, whereas in our human world, like trees tend to grow up, these trees in computer science tend to grow down. I just couldn't fit this all on screen here, but let's, for instance, call this thing our root. So this is our root of our tree, and to the left of it, it's a child, and to the right of it, it's right child, or more generally like a whole subtree, and a whole right subtree, a left subtree, a right subtree. Because indeed, like if we start at 42, we have another tree of sorts. Okay, so root of that 42 is a child down here called 23, and another child above called 50. So in this case, like it's each of those nodes in our structure, otherwise known in computer science as a tree. Again, they have 0, 1, 2, or however many more children. You can actually create that second dimension. That gives you the ability to preserve not only the ability to add data more dynamically, like 50, 51, 52, but also we now gain back that ability for us to search. So after all, like if I'm asked a question, is a number 15 in our structure? Well, let me check out for you. So I'm starting at 16. which is where, the roots is where the structure will begin. Just like the linked list will start conceptually at the left, I'm going to go and check 16 as the value that I want. If I'm looking for 15, no, it's too big. 16 is way too large. But I do, if I know that 15 does exist, I know that it's going to be off to the left somehow. So I'll do that, of course. Now 8, of course, that's not the value I'm looking for either. But 8 is smaller than 15, so I'm going to go off to the right. And sure enough, if I do find it, they go 15. It only took me 2 steps to find, not n to go off and find it, because even though I did have this second dimension to the left, I am able to lift up some of those loads rather than draw them down as a straight line, as a linked list all the way from left to right. So within the second dimension, I can start to organize things a bit more tidily. And so that's one of the key characteristics of this tree. It's generally known as a binary search tree, not only because it's a tree that lends itself well to search, but also because each of those nodes has no more than 2, or by children, 0, 1, or 2. And notice that to the left of the 16 is not only the values 8, but every number that can be reached to the left of 16 happens to be by design less than 16. And that's how we found 15. Moreover, to the right of 16, every value that is greater than 16, just as we have here. And so by definition, we can apply so-called recursively. We can make that claim about every node in that tree, because here, like 42, every node to the left of 42, albeit it's just one less, every node to the right, albeit it's just one more. So long as, you bring to bear that data some amount of intuition that we brought about in our phone book and our dictionary, we can achieve those same properties on our goals. This efficiency of logarithmic time, log base 2 is indeed like how long it might take us then, big O, to find or insert some value. Now, to be fair, again, there are some prices to be paid here. Like if I'm not careful, a data structure like this could actually devolve into a linked list if I just keep adding and by coincidence or indents more and more big numbers. They just happen to be getting longer and longer and longer and actually stringy unless we're smart about how to rebalance the tree and occasionally. But yeah, there are other forms and other of these trees that are smarter. And again, with code, they will be able to rebalance themselves just to make sure they don't get really long, very stringy, but just stay as high as possible, okay? There is another price to be paid here, which is more space, okay? So whereas my array used no arrows whatsoever because there was no arrows to be thinking of, okay, therefore no extra space. My linked list did use an extra chunk of memory of space for each node, storage of the point and also the address of the neighbor. So there's 2 things to keep track of. In a tree structure, again, if you're storing multiple children here, you might end up using as many as 2 more chunks of memory to store, if not 2 more of those arrows. And so again, with a tree structure, you're spending more space, but it's potentially saving you more time. So again, we do see this trade-off ultimately. If you really want less time to be spent, you're going to have to spend more of that space. Not all is hopeless though, because there is one last thing. So again, with an array, we had instant access to the data. We painted ourselves a bit into a corner there with the array. With linked lists, remember we did solve that particular problem, but we did give up the ability to jump right to where we wanted to with a linked list. With trees, particularly binary trees, search trees, we can arrange our data smartly and we can regain that logarithmic time. But wouldn't it be nicer if we could just achieve even like better, say, constant time searches of data and insertions thereof? And well, for that, perhaps we could amalgamate maybe some of the ideas we've seen thus far into one really cool, clever data structure. And I'm going to call that particular data structure this thing of a hash table. And like perhaps this is in theory, this is the holy grail of data structures. People love a hash table, hash map, hash map. But an idea that you can basically store anything inside of a hash table ideally in a constant time. Okay, how do we begin to do this? So let's go back and let's consider ourselves to be, an array. And again, this array this time I'm going to draw vertically. This simply just implies that we leave ourselves a bit more room for something clever. Okay, so this array, as always, we're going to index our array in simply just by way of those locations earlier from here. So this might be location 0, this might be location 1, followed by 2 or 3 or any number of others as well. Okay. Now, how am I going to use this array? Suppose then that I want to store now names, people in chat today, not just numbers. Those names, of course, like they could just be inserted in any location, but if unsorted, we already know we're going to suffer as much as big O of n time, linear time with as much as, with which to find a particular time in that array if you know nothing a priori about the order. But, well, we already know too that we could do better, like just like the Yellow Pages, just like a phone company, just like a dictionary would. If we sort all the names just by putting them into the structure, we can at least then do a binary search and whittle down the search time to log base 2 of n. Wouldn't it be nice though, if we could whittle that down further and maybe get that to maybe near constant time. Okay, so maybe like 1 or maybe 2 steps or a few steps at a time. Well, with the hash table, you can do this. And you can approximately or ideally do this, okay? So long as we decide in advance how to hash those things, in other words, like those words, those strings of characters, I'm going to just use names as an example, but they have letters inside of them, say like Dennis. So what if we looked at not the whole name, but just the first letter of that name, like a dictionary, okay? Which of course, like constant time to start, just to look at one value. So if D is the 4th letter in the alphabet, in the English alphabet, if I store Dennis, or really just any D, the 4th index of the array, that's going to be a location 3 if you start counting off from 0. So here might be the A names, there might be the B names, here might be the C names, and then someone like Dennis at the bottom, this belongs in this bucket, if you will. Suppose that I want to store other names in the structure. So I'm going to say that Alice belongs at location 0, Bob belongs at location 1, and if I continue down this logic, I can insert more and more names, so long as we start to hash those names and we jump right to that location. After all, like I can, in one step, look out for A or B or D and instantly know like 0, 1 or 2 or 3. How can I do this? Because remember, like in the world of computers, you have ASCII or you have Unicode. So, you have numbers which are going to be predetermined to map to some characters. Now, to be fair, like I'm pretty sure 65 was a capital letter A. B was 66, 60, and so on and so forth. Okay, so we could certainly subtract maybe like say 65. There you go. I could take away 65 from this in order to get back to 1. So I can at least look then at the first letter of my name if my name was A, and then convert that into ASCII and then subtract from it quite simply 65 if it's capital letter A to get precisely to the index that I want to. Now, to be fair, that's not one, but that is 2 or 3 separate steps. But that is a constant number of steps again and again, independent of n, of the total number of names. Now, what's really nice about this is that we have a data structure into which we can insert more names simply by hashing them and getting out as an output that number of the index, 0 all the way to 25 in the case of the English alphabet. But what problems might arise with this? The catch, though, is that if we have someone else, though, for example, let's say Daniel. I forgot the name for a second. Now, how do we give Daniel its own space? Like if I'm trying to put Daniel into this array, the catch though is that Daniel, whose name also happens to start with the same letter as well. Unfortunately, there's no room for this at the moment, right, in my data structure, since there's already there. Dennis is already there. So maybe I can draw inspiration from the other structure still, is maybe we can put Dennis or Daniel in this array, but not even treat it as an array, as like the entire data structure, but really only the beginning of another structure. In fact, let me go ahead here and I'm going to put Dennis beside, or really give him his own box, and then give Daniel his own box as well. Now, Daniel and Dennis are really just nodes in a structure. And then we can get this array still to get to the right of the nodes of interest, like this. But of course, we can just use arrows against the system altogether, so that if I have multiple names, each of which starts with the letter D, I need to remember the link to those nodes together, thereby allowing myself to have any number of names that begin with that letter D. treating this as a linked list, ultimately. But I get to that linked list instantly by looking at that first letter, jumping here to the right location, and then simply here, I get that dynamic growth, get that instant access to the list, thereby decreasing significantly the amount of time it takes for me to find someone, maybe 1/26th the amount of time. Now, to be fair, wait a minute, I'm already showing you collision, so to speak, where I have multiple inputs and they are hashing to the same output, 3 in this instance. In the worst case, perhaps, everyone in the room, everyone here in Zoom has names that begin with the letter D, which really means you don't have to have a hash table kind of any array at all. You really just have one long linked list, and thus it would be linear. But that would be, a corner case. That'd be more of a perverse scenario where you should just try to avoid that by the way of the hash function. Like, if that is the problem that you're facing, then your hash function is just as bad. Like, you should not have only just looked at that case, but perhaps not the first letter of every name, but perhaps you should look at the first 2 letters of every name, so back to back. Therefore, like, everyone's name that begins with a DA in one list, DE in the second list, DC in, and any number of other those. So, a different list altogether. So DD, DE, DF, DG, and so forth. And actually have just multiple combinations of every 2-letter words. Have as many buckets, so to speak, have many indexes in your array as there are pairs to alphabetical letters. Now, again, to be fair, you might have, again, people whose name begins with a DA or the DO or DE, but hopefully there's even fewer than that too. Like, as I said, a hash table, this whole structure is great. It kind of approximates the idea of constant time because it devolves into places to linear time where there's a longer list of names. But if your hash function is good, and if you don't start to have these all the collisions together with names, therefore, ideally, you don't need to have as many linked lists in them, just the names themselves, and then you actually do have a structure that looks like this, that does give you constant time access, but ultimately combining all those underlying principles of dynamic growth, of random access that we're looking for, ultimately the storage of all your values in there. I love hash tables. So then how might we do this in say, Python? How might we implement this data type in like int and str? Well, in the case of Python's latest version, like this allows your strings to grow as big as you need them to be, and so it can be surely that only using contiguous memory once it's allocated that stays in the same place. If I want a number to grow over time, well, you're probably going to need to, again, in advance, allocate some variable number of bytes in that memory. Strings too, by the way, if you want to allocate strings, you need to allow them to grow, which means like you need to find extra space in proximity to the characters you actually already have here. Maybe like relocating the whole structure so you actually have that value that keeps on growing. But how to? We can do this without counts of memory, in that particular language, even if it isn't necessarily of interest to us. Like we just know that it can, even underneath the hood, how we might do so. As for the other values, like in other structures like Python or dict or dictionary or list, well, those two are exactly like we've already seen. A dictionary in Python is essentially just a hash table. So in Python, that's sort of just a variable that indexes on not necessarily numbers, but words. And by those words, can you get back a value? Indeed, like more generally, does a hash table have keys and values? But words, by those words, can you get back a value, like a key value pair? So those keys are going to be inputs by which you generate some output. So in our data structure, you might have the names as inputs. The output of my hash function might be an index number, like a number or like an address or a space. And so in Python, you do have this wonderful abstraction in code. This is why it's a simple language that allows you just to express that idea of associating keys with values, names with a yes or no, or a true or false, all these things in a way so you can ask those questions yourself in code with just a word or really just a short sentence thereafter. As for the list, by the way, it's quite simply this. A list is simply just the idea of an array, but with that added dynamism, okay? And that's like a linked list of sorts. Okay, looking at the time, I think I just got dead on 10 o'clock. This high level of code, again, I'm trying to get you to think not only computationally, but express yourself algorithmically, knowing yourself and trusting that the computer can do that bidding that you want to. How the data structures and organized, really, that is the secret sauce that these languages, these tools, indeed, when you go off and have some backend, when you have some systems, some database, some work to be done that underlies those systems, ultimately boils down to not only the algorithms in use, but also the data structures that underlies them. Because together, and we've seen this, they combine to produce not only the correctness of the answers that you want, but also the efficiency by which then you can find and use and retrieve those answers hitherto. What I'm going to leave you with that is a thought. I have some that I can chat. These 2 links are also mentioned in the document I just sent you over. But if you are interested in this discussion, I'm going to pick this up further. And next week, talk about blockchain technology and how we can arrive at something like Bitcoin. There is a phenomenal video that inspired me to kind of get into this line of thinking. I'll discuss this again more next week, how Bitcoin really works. But it is... Ooh, thank you, David. Yeah, using AI models to generate exploits for cryptocurrency.
Yeah, I just came across that one and thought you might be interested.
So, what does it mean? Smart contracts with no other name. Okay.
It's not a simple thing. It's just done by universities, but it's just showing that there are exploitable bugs in the implementation of smart contracts, and they found a way of exploiting it. And theoretically stolen a lot of money with it. I say theoretically because it's universities at the end of the day.
Yes, it starts off in kind of these discussions. In a place where it can demonstrably be done, will inevitably sprinkle its way into the training data set.
Yeah.
And this AI models at least are familiar with these things. And if not, it just kind of contaminates the world of bug bounties too, where it's becoming more and more problematic that people who will search for common vulnerabilities and exploits will often use AI to kind of hallucinate those problems to begin with. Most of the time they're wrong, but occasionally they are right. And there is a big discussion to be had around that, which is AI is maybe better at us than finding patterns and understanding data. But also it needs the human criticism. We need to peer review these things better because it's already soaking into the training journal. It's already kind of these M dashes too. They're driving up the bloody wall. Those things there. They kind of snowball into into the real integrity of what we have as our the last holy grail of data, which is peer reviewed journals and scientific papers. If that gets exploited, who knows? I'm wondering what actually happened here. This is okay on Ethereum and Binance. I would need to understand what they accomplished and how. But this is a really good article in the fact that I'm going to look at this next week. Again, I'm not going to say too much, but I've been working on this one for a while. So we'll talk about Bitcoin next time we're together. But yeah, this is great. I'm really glad you brought this up. Thank you. I'm just saying as well, Dennis popping off. Valentine as well. Others as well too in chat. Thank you as well for the evening. It's been phenomenal. Hopefully you've had a good session with me. Again, these things are dense, but I'm trying to get through them as quickly as possible so that you can then make the most of these sessions or come prepared for not just cloud more generally. How did you find this out of curiosity?
Well, the Register is just one of the IT online journals that I read.
What journal is it, can I ask?
The Register. That's
the Register, I see. Yeah, I'm always on the lookout for things like this. I am in the daily.dev side, so I get kind of my social feed this way. But it'd be good to know if that was one of them. At least I'll keep an eye out for that, the Register. Probably has been mentioned before. There we go. Nice one. Okay, as I said, I'll look into this a bit better. I'll follow them, understand what's going on. Yeah, cool. Manfred, thank you very much. Alex, good to have you. Chantel, as well, Marceli, Manfred, Dave as well. Been a pleasure. I'll see you next week. Have a wonderful weekend and enjoy your time. Live both ways across the road, eat your vegetables, drink water. Say please and thank you, and I'll see you soon. All right.
Yeah, you too, Malcolm. Yes.
Thanks so much, David. Alex, Marceli, Mohammed. Take care, pal. See you soon.